So let me use the remaining setup to talk about pendulum as a simple harmonic oscillator. So, pendulum as simple harmonic oscillator, and I guess my goal is to analyze this pendulum setup to come up with a description for this that I can say is come up with a description for this that I can say is gives me an equation of motion that looks like the equation of motion of the spring system that you already saw. So, so let me write down the goal. Goal is to derive equation of motion that looks like simple harmonic oscillator equation of motion. And as a reminder, this is for the mass on a spring. This is what that equation of motion looked like. Simple harmonic oscillator equation of motion. It looks like, let's see, double time derivative position, acceleration was equal to minus k over mx. Right? This was the equation of motion that we got after going through the standard strategy stuff. Okay? So we are going to come up with that for this pendulum. Let's hope this doesn't fall off. For this pendulum. So where would the analysis start? Where would you start for analyzing this? Yes? Okay. We can imagine it being present at one of its positions. Top seems like a good place, so let's start from here. So I'm going to, whenever you're doing a problem, you'll find that it's good to have a diagram. It'll help you think of approaches that you might not have thought if you never looked at the diagram. So I have this mass at this height. I guess it's described by, there are different ways of describing it because this is something that moves like this. If you want to describe in terms of energy, then what you might more intuitively use is this change in height, right? But if you're trying to parameterize this motion, you'll find that it's actually better to use this angle. Because angle is a single parameter that changes at a more, I guess, not predictable, simpler rate than this height. Because if you want to figure this out, this height, it involves, it involves trigonometry, and like it's harder to compare. So without too much explanation, I'm going to decide to use this theta as my coordinate variable, as the parameter I'm going to use to describe the motion of this. Oh, here's one way you can look at that maybe doesn't require too much explanation. Does it make sense to describe this as a kind of a rotation? The rotation, right? This is at a fixed distance from that fixed pivot. So it's it's not going over one full rotation, but it's going over a kind of a rotation. Okay? That's why I'm going to say this theta is a better way to describe this rotation. Good. So use theta to describe rotation. All right, so once you've made all that decision, what kind of equation would you want to write down? I mean, so you decide you are going to describe this as a rotation, analyze it as a rotation. Torque. So you want to describe torque here now. Because what you are looking at, okay, so what causes it to rotate, it's going to be torque. So you have to draw a free body diagram. You are going to go through standard strategy again. So you draw a free body diagram. Let me sort of draw it this way. This is my center of rotation. This is my massless string. And here's my mass. Let me express my mass as a point mass at this distance. So I probably need to know something about the distance. This has some amount of mass m. I need to draw actual forces. What are the forces on this system? Yeah, there's going to be gravity. mg pulling it down. Any other forces? Yeah, so there's tension. Or I guess if you're looking at the mass especially, there's tension pulling that way. Anything else? And I guess if you wanted to be really thorough, you could, looking at this as a system, you can draw a force here. But actually, let me not do that. I'm just going to describe the mass. So if you're describing the mass, you have gravity and tension. Now, what I'm going to do is, because I'm describing this as rotation, I'm just going to focus on torque. I'm not going to write down the net force. I'll just describe torque, net torque. So does it seem reasonable to pick this as my center of rotation for calculating torque? Okay. Does tension generate any torque then? Yeah, the lever arm for the torque is 0 because imagine extending torque into a straight line, it goes right through that point. So torque generates 0 torque. Torque. Too many T's. Tension generates 0 torque about this fixed point. So the only torque is going to come from gravitational force. So I need to figure out my lever arm. So my lever arm looks like this. This is my perpendicular distance or lever arm. So let me write down torque this way. Torque is equal to the gravitational force, mg, times the lever arm. I thought I was going to use theta to describe my rotation. I don't see any theta there. I probably need to rewrite my lever arm in terms of this length and theta. Anybody know from staring at this diagram how the lever arm and L are related?
Yeah.
How are they related?
That's theta, so that R is R sine theta.
Yeah, so this lever arm is equal to L sine theta. So if you haven't seen it yet, then the best way to do is keep drawing on your diagram. So this is the theta that we labeled. So I guess I'm looking at this triangle here. So this theta is equal to this theta. So this is the opposite side with the L being the hypotenuse. So when you have to work out geometry, it always helps to draw it. It's harder to imagine in your head. So this is mg L sine theta. All right, so that's torque. I need to describe how this torque changes, how it causes things to rotate. So this is equal to rotational inertia times angular acceleration. Good. All right. I guess I'm going to do the same thing I did the last time. So this was acceleration, and I expressed the acceleration in terms of position and time, because when you look at this as one equation, I have two unknowns now. I have theta and alpha, and I want to describe it in terms of a single variable, not theta and alpha. So I'm going to write angular acceleration in terms of the angle. So I need to say this is equal to I times the angular acceleration is rate of change of angular velocity. Angular velocity is the rate of change of angular position. So this is the second time derivative of angular position. So second time derivative of angular position. Now, when you look at this carefully, you will notice that this doesn't look exactly like that, because the simple harmonic oscillator equation of motion that we looked at before has this minus sign. And if you recall back to Tuesday, that was actually important. There were some forms of function that we could have considered that we ruled out because of this minus sign. And when you look at this, I don't have any minus sign anywhere. So I must have made a mistake somewhere. So that's where you have to be careful with the directions. So sorry, I get neurotic and think I didn't start recording. So I wasn't careful with the relative direction of theta and alpha. So imagine you are looking at this system from over here. When I make this move this way, my theta, is that in clockwise direction or counterclockwise direction? Imagine you are looking from here. Counterclockwise? Clockwise, right? Yeah, clockwise. Okay. So, all right, so that's my angular displacement, clockwise angular displacement. When I let go, what's the direction of angular acceleration? Counterclockwise. So I did not account for that in my equations. The fact that the direction of my theta is actually opposed to the direction of angular acceleration. So I guess the best way to fix it is this. Let me say, so keep this, and I'm going to be careful in putting in the signs for the torque. To say, so I will put in signs here, minus, and minus here. And this is what really, this is actually a little bit of a departure of how I do things normally. Because normally, when theta is, normally so here I'm allowing theta to become negative. So when theta is clockwise, I'm letting theta to become negative. Whereas normally in this class, the way I've done things so far is when I know some quantity is negative, I actually pulled it out, made the parameter positive, and put the negative sign in the equation itself. That's how you end up with a positive sign here normally. But because we are doing more formal mathematics, what I'm doing now is I'm going to allow these parameters to become negative and say that theta, well, if it's negative, then it is a negative value. I'm not going to try to pull that negative sign out. And instead, to express the relationship between these two, I'm going to put in a minus sign here so that when theta is negative, then negative times this negative will give me a positive angular acceleration. Okay? So this is the equation that I should have written out. Good? So, all right. I guess let me do a couple simplifying things. So I guess, yeah, it's not going to be as general as I'd like it to be, but this will make things easier. This rotational inertia I know what it is. So might as well plug it in so that some of the things can cancel out. Good? The rotational inertia here, it's a point mass at a distance L. So the rotational inertia I here should be mL squared. Good? You see some things cancel out when you do that. Let me write down the version with the things canceled out. Masses cancel out, and the L squared cancels out 1 over L. So you end up with G sine theta, minus G sine theta is equal to L times the second time derivative of theta. Okay. All right, let me solve this for the second time derivative because that's what we've been doing before. Then we'll be able to see, does this equation of motion look anything like the simple harmonic oscillator equation of motion? So solving this for the second time derivative, we get that's equal to minus G over L times sine theta. And this doesn't look exactly like this, right? So, I mean, we got some parts right. We have minus sign there, we have minus sign here. We have constant coefficient here, we have constant coefficient here. But the thing that should be causing you a little bit of a trouble is this last term, sine theta. Because this is just x, not sine theta. And having x here actually was important last time also. Because in looking for the solution, this is what we said to ourselves. Like, what function do I have? That if I take two derivatives, I get the same function back. Now, imagine asking yourself this question. What function do I have that if I take two derivatives of it, I don't get the same function back, but I get the sign of the same function? Do you know any function that behaves like that? I don't. Like, when would you ever get sign on top of what you have from taking a derivative? Like, that never happens. Unless it doesn't happen with any well-behaved analytical or special functions that you know. If you had one, well, this would be the equation that you use to define the special function. Mathematics actually does that from time to time. So this is the point where we have to use approximation. So here, with the mass on a spring, everything we did was an exact calculation. With the pendulum, it turns out if you want to treat it as a simple harmonic oscillator, you can only do it approximately. And let me tell you that how that approximation happens. So for what you were seeing before, when it's going over small motion, well, smallish motion, I can treat this as a simple harmonic oscillator. But once, all right. Once the motion starts to become large, I'm a little bit afraid I think something might break again. So cover your ear if if you're sensitive. Once it goes into larger motion, yeah, that's what I thought would happen. Okay, all right. So I don't. Let me get my safer pendulums. So this is the approximation that we are making, and it's important that you understand the conditions of approximation. So when this is undergoing small motion, we are going to say, oh wait, by the way, now that I don't have a pendulum, never mind. When it's a small pendulum motion, we can say, okay, this looks like a simple harmonic oscillator. But once this motion becomes larger, then that's where this approximation that we'll make will break down. So this particular form of approximation, it's called a small angle approximation. You might have heard it before. Small angle approximation. I have not mentioned it yet, but I think this comes up in your textbook actually. How many here have seen the phrase small angle approximation? Yeah, so you might have seen it as you're reading through the textbook, working through, probably not homework. And you might have actually, how many have seen small angle approximation in your calculus class? Okay, yeah, that's probably where you would have seen it. How many here have have taken Math 3B? How many are currently taking Math 3B? Okay, so this is something that you will see in your Math 3B. Have you covered the Taylor polynomials yet? Have you seen it in the syllabus that it will come up later in the semester? Infinite series. Taylor polynomial is on. Okay, how many have you have seen series in your calculus class, right? There's an infinite series. And one of the mathematical methods you cover in calculus is how to approximate a function by an infinite series of polynomial.
Learning it right now.
Yeah. So an example of that is something called a Taylor polynomial. Let me write down Taylor polynomial approximation of two of the functions that you know, sine of theta and cosine of theta. And you will see this in your math class soon if you haven't already. The Taylor polynomial of sine theta, I'll write down the first three terms or so, maybe four. It's equal to, or it's approximately equal to theta minus theta to the third power over 3 factorial plus theta to the 5th power over 5 factorial, and I guess one more, theta to the 7th power over 7 factorial. You begin to see the pattern, right? And you do that with the Taylor polynomial, you take the derivatives and there's all of that there. Similar for cosine theta. Cosine theta can be approximated as 1 minus theta squared over 2 factorial plus theta to the 4th power over 4 factorial plus, minus theta to the 6th power over 6 factorial, and so on. These are infinite series, by the way. If you want exact result, you have to go infinitely long. So the approximation step is where we do not go infinitely long. We look at how many terms do we need for a good enough precision. Let's say your criterion for good enough precision was 5%. If you get a number that's within 5% of the correct answer, then you say that's good enough for me. So that's the idea behind the approximation. You know your answer is wrong, but you know it's not too wrong, and it's good enough for you for what you're trying to do right now. So let me give you some sense of how good small angle approximation is actually. So let's say we want to be within 5%, so we want 95% accuracy. So at what angle do you think we'll be coming up to that? So if we have, so this is the approximation that we are going to be making. We are going to be approximating sine theta with just the first term, just the theta. And often, usually, we are going to be approximating cosine theta with just the first term, just 1. So let me ask you, so if you're trying to describe, so let's see, how large an angle do you think I'll need to go before the cosine, so cosine theta of 0 degrees is 1. How far do you think I'll need to go before that begins to be wrong a lot? As in, it's so where I'm at some angle, so this is the question I'm asking, at what angle? So going from 0 degrees to at what angle, theta, would you find that, so cosine of 0 degrees, this length here was 1. And at some angle, this length here, you will get, instead of 1, you will get, let's say, 0.95. That's where you are off by 5%, right? So at what angle do you think you'll get to that point where the distance from this point to the ball isn't, or the height of the ball isn't 1, but it's 0.95? Like how much of an angle? Like 1 degree, 5 degrees, 10 degrees? Oh, sorry, 1, 5, 10 degrees, 30 degrees? Yes? So it's 30 if we are using sine as a parameter. Yeah. So it's actually, this is 30 degrees. It's pretty large angle where this sine theta small angle approximation is correct within 95%. With the cosine theta, it's a little bit smaller, but let me just show you the number. So it's easier to work out this number in radians. So let me actually approximate, you know what, I think it's quicker to do it this way. Let me do it on Wolfram alpha, because I got other stuff I want to talk about today. So, so we are going to solve cosine of x is equal to 0.95 for x. Oh, I could have done arc cosine. Oh, never mind. That's probably what I should have done. In fact, why is it not giving me a numerical value? Yeah, never mind. I should have just done arc cosine. Arc cosine of 0.95 in degrees. Or, so arc cosine 0.95 in radians, it's 0.317. So you might think, oh, that's a small number, but that's in radians. In degrees, this is how big it is. You can go up to something close to 20 degrees before cosine of that angle will be still more or less 1. And if you're dealing with the sine, because you have this 3 factorial instead of 2 factorial, you can go to even larger angle. You can go up to 30 degrees and it'll still be 95% correct. So this is the approximation that we'll be making. This approximation is necessary here, because otherwise the remaining calculus that we want to do is too difficult. So using small angle approximation, we can write it this way. We can say instead of this, we can say that the second time derivative of theta is approximately equal to minus g over L times theta instead of sine theta. So with the small angle approximation, you have this form of the equation. Now this does look like this. This is your parameter, theta. So this is your parameter, x. What the simple harmonic oscillator said before was you take the parameter, take two time derivatives, then you get minus times coefficient times your parameter back. Here, parameter, two time derivatives is equal to minus times constant coefficient times your parameter back. So mathematically they are identical. All the solutions to this would also now be solution to this. So we can say, so we can say solution to this will look like something like this. We can say it'll look like theta is a function of time, will be some amplitude times cosine of omega t plus phi. So you'll get the exact same form of the solution. And finally, this is one additional thing that we can say that I expect you to know for exams. This particular coefficient was related to angular frequency, natural oscillation frequency. This was equal to omega squared, or solve it for omega, this is what you got. And because the mathematical forms are exactly the same, we can say that this coefficient here, in the same location where the other coefficient was, we can say that this is also equal to angular frequency squared. So in other words, natural frequency of oscillation for pendulum, I should really call this a simple pendulum. Simple pendulum is equal to square root of g over L. And that's what you saw before. When you have this particular pendulum, it oscillates at a frequency. Like, starts from here, 1001. Wait, I need to. 1001, 1002, about 2 seconds period. And when I make the string shorter, then it'll oscillate, let's see, L is smaller, so omega will be larger. 1001, 1002, 1.5 seconds or something. So that's why here, when they were still standing, when they had a different length, you saw that they had a different natural oscillation frequency. So oscillation of one didn't cause the other to oscillate at large amplitude. Good? Questions? Comments? So that's the pendulum. I guess going over that took longer than I was hoping. Yeah, so I think there are some homework problems on pendulum systems. Make sure you know enough about it. I think one thing that we didn't have a lot of time in class is looking at the energy of a simple harmonic oscillator. And it's a sort of application of what you know. So my advice to you would be look at the homework questions. To the extent that it's covered in homework is what you are supposed to know. Okay?